Hello students, this is lecture number 12 and this is about response of LTI systems to complex exponentials. We have already discussed what LTI systems are, their properties, and we also know what complex exponentials are, how they are mathematically represented. Now we'll apply complex exponential as an input to the linear and time invariant systems and we'll compute the output. The purpose of this lecture is to build the understanding towards more advanced topics like Fourier methods and the Laplace methods. We already know the advantage of representing the signals as a linear combination of basic signals. During the lecture of convolution, we represented any kind of input as a combination of impulses, right? And the advantage of doing that is that the set of basic signals can be used to construct a broad and useful class of signals. We can represent any kind of signal using the basic signals which are very known to us. We know their mathematical models clearly and they are very easy to handle. Like impulse signal is very easy to model. It is a well known model, it is a very famous signal, everybody knows about it, and it can be easily represented mathematically as well as graphically, and also the response of the system can be easily determined. So this is what happens when we represent the signals as a linear combination of some basic signals. And the other thing that we get, the response of an LTI system to each signal can be easily determined because LTI systems follow the principle of superposition. So determining the response of the system when we represent input signal as a combination of basic signals is easy to determine, right? We can break the signal into different parts and represent each part by another some simple and basic signal and determine the output for each signal separately and then combine the responses to find out the combined response, right? So this is actually a usual practice in signal processing techniques because the actual signals maybe they are very large or maybe they are complicated or it is very difficult to define those signals mathematically by a single equation, right? So it is better to break the signals into different parts and then define them using any basic signals like impulse, step, or for let's say in this lecture we are going to represent the lecture using complex exponentials. So both of these properties are provided by a set of complex exponential signals of the form e power st, where s is a complex number, so that makes it a complex exponential, right? So when we can get both the properties that we discussed in the last slide. That the first property was we can represent the input signals using the combination of exponential signals, so we can do that. And second, the response of the signal can be computed by computing the response of the system individually when the exponential or the sinusoids are applied separately, and then we can combine. So we can actually achieve both of these properties using complex exponentials. And why we can do this? Because response of an LTI system to a complex exponential is also a complex exponential. It is always sinusoidal. When a sinusoidal input to LTI system is applied, the response of the system is also sinusoidal of the same frequency. This is the fundamental property of LTI systems. So when we represent the input signal as a combination of sinusoids, complex exponentials, the output can also be represented as a combination of sinusoids, right? So this makes it mathematically more convenient and somewhat easier to compute the response of the system, right? So when the complex sinusoid suppose e power st is applied as an input to the system, the response produced by the system is e power st, the sinusoid of the same frequency, multiplied by some amplitude factor h of s. Right? So h of s is a complex amplitude factor because s is a complex number. So here this e power st is called the eigenfunction of the system, and h of s is called the eigenvalue for any value of s. Right? So a signal for which the system output is times the input is referred to as an eigenfunction. So here the system response is input multiplied by some constant, right, h of s, which is a complex constant, right. So that input is called the eigenfunction, and the complex exponentials are basically the eigenfunctions of LTI system, right, because LTI systems are represented by ordinary differential equations, and the solution of ordinary differential equations are actually exponential functions, and the complex constant that is multiplied with the eigenfunction is called the eigenvalue for any particular value of s. Now to show that the complex exponentials are indeed the eigenfunctions of LTI systems, let us consider an LTI system having an impulse response h of t. Right? Now let us apply an input in the form of complex exponential to this system and compute the output using convolution. So let's say the input signal that is being applied to this LTI system is e power st, and now we can compute the output using convolution integral. So the convolution integral formula is given by y of t equal to integral of h of tau into x of t minus tau deta from minus infinity to infinity. So h of tau and x of t minus tau can be replaced by this complex exponential. So let us substitute the values in this integral, get e power s into t minus tau. Now further simplification is possible by separating the powers of exponential. So e power st can be separated, and e power minus st can be written as separate exponential. Now e power st is constant, right? It can be taken out of the integral, and further now e power st is constant, and integral of h of tau into e power minus s tau is a function, basically is the Laplace transform of h of t, right. So if you remember the Laplace transform, and the transform of any function is integral of that function and multiplied by e power minus st, right. So this basically is the Laplace transform, and this integral will converge if h of tau is stable, it is bounded, right. E power minus st is already bounded, it is decreasing exponential. So h of tau, if it is bounded, if it represents as if it is the impulse response of a stable system, then this integral would converge, and let's say the this is actually the Laplace transform of impulse response of the system, and the transform is represented by h of s, and e of st would be multiplied as it is. Now this is the expression for the response of the system, and you can see the input est has appeared as it is in the output, because it is the eigenfunction, right, and it is multiplied with some complex constant which is the eigenvalue of the system. So this proves that complex exponentials are eigenfunctions of LTI systems. The constant h of s for a specific value of s is then the eigenvalue associated with the eigenfunction e power. Now the usefulness of decomposing any signal, input signal, into eigenfunctions or the complex exponential can be understood from the following example. Suppose x of t is a signal which is the linear combination of three complex exponentials, right? So x of t equal to this is the first complex exponential, this is first complex exponential, second complex exponential, and third complex exponential. So x of t actually is a signal which is decomposed into combination of complex exponential, or we call it linear combination of complex exponentials. Now the response of system due to each exponential separately, for example a1 e power s1t is first applied, the response of the system should be a1 h1 of s1 and e power s1t, right, where a1 is any constant, right, and s1 is some value of s, right. So using the linearity and scaling property of LTI systems, you can write down the response of the system due to this exponential. Similarly, the response of system to each exponential is separately obtained. Now you can actually find out the response of the system by adding all these responses. The response of the system would be sum of the individual responses, and that can be written in using this expression. Now this implies that the representation of signal as a linear combination of complex exponentials lead to convenient expression for the response of an LTI system, right? So this proves that when complex exponentials are applied at their input, then output can be easily calculated because we know the response of the system would be same as the complex exponential applied at the input multiplied by some complex constant. So generalizing it, if input x of t to an LTI system is represented as a linear combination of complex exponentials, x of t is a k e power skt, where k can be 0 to infinity, whatever, the response of the system would be k a k h of sk and e power sk t, where h of sk is the transform of the impulse response of the system, right? So this actually is very mathematically very convenient, right? When we represent the input signal as a linear combination of complex exponential, we can directly compute the output using this property. So if the input to an LTI system is represented as a linear combination of complex exponential, then the output can also be represented as a linear combination of same complex exponential signals as mentioned in this expression. Now let us solve an example to enhance the understanding regarding this topic. So consider an LTI system for which the input x of t and output y of t are related by this expression, right? So y of t is equal to x of t minus 3, where x of t is the input and y of t is the output. So this is basically a delay system, right, that introduces delay of 3 units, and we have to determine the response of the system when a complex exponential e power 2j_t is applied as an input, right? So we know we can compute the response of LTI system using this general expression, where e power st is the eigenfunction and h of s is the eigen value, which is complex constant, and h of s can be determined as this. H of s is basically the Laplace transform of h of tau, and h of tau is basically the impulse response of the system. So response can be calculated using this equation. So we already know what is eigenfunction, which is given by this expression e power 2j_t, and now we have to calculate h of s, right? For h of s, to know what is the impulse response of the system can be determined from the input output relationship, which is given by this expression y of t is equal to x of t minus 3. So when input is impulse, the output of the system is called the impulse response, right? So in this expression, instead of x of t minus 3, we will apply the impulse, which is delta t minus 3, and the resultant output would be the impulse response, which is h of t equal to delta t minus 3. Now we can compute h of s by evaluating this integral. So substitute the values into this and evaluate the integral, you will get the value of h of s. Now, you should remember the shifting property of impulse, that is given by this integral when any function g of t is multiplied with shifted impulse function, and integral is taking from minus infinity to infinity. The output is simply the value of that function at t equal to t naught, right? So this same property can be applied here to find the value of h of s, and which came out to be e power minus 3s. Now we can substitute the values into this expression. We know the complex exponential which is applied at input is e power j2t. So writing down, instead of e power st, we write down e power j2t, and h of s is e power minus 3s, and s here is equal to 2j. So s is equal to j2 and y of t equal to h of 2j e power 2j t. Now h of 2j is simply e power minus 6j and e power 2j t as it is. So this e power 2j t is basically the eigenfunction, and this constant, the complex constant, is called the eigenvalue. So e power minus 2 of the system, jt is eigenfunction, and e power j6 is the associated eigenvalue. And now we have another similar example, and in which we are applying input signal, which is a combination of two cosine functions of different frequency. One is cos 40 and plus cos 70. So first what we need to do is to represent x of t in terms of complex exponential, because this is represented in terms of trigonometric functions, right? So here you can see in this formulae we need to know the complex exponential representation of the input signal. So let us first represent this input signal in terms of complex exponentials. So we know from the popular Euler's formula that cos theta is equal to e power j theta plus e power minus j theta divided by 2. So using this formula, we can actually represent our cosine functions in the form of complex exponentials. So cos 4t is represented in this form, and cos 70 is represented in this form, and further simplification would result in this expression. So the impulse response of the system is same as the one we solved in the example number 1. In fact, the system is same as example number 1, and only that input that is being applied is different. So h of t and h of s would be same, exactly like we did in example number 1. And now actually we know value of h of s, and we have represented the input signal in terms of complex exponentials. So we can actually write down the expression for the response of the system y of t, which is equal to h of s and multiply by the input complex exponential. Now solving it further by multiplying corresponding eigenvalue with each complex exponential. So h of s multiplied with this would be h j4, h of s multiplied with this would be h minus j4, h of s multiplied this would be h of j7, and similarly for this would be h of minus j7. Now let us substitute the value of h of s e power minus 3s in output expression. Now instead of h of j4, we can write down e power minus j12, right, because s in this exponential is equal to j4, right. Similarly, the value of s for this part of exponential is minus j4, so it would be e power j12. The value of s in for this exponential is j7, so e power minus 3 into j7 would be e power minus j21, and similarly this would be e power j21. Now simplify it further by adding the powers of exponential here, 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 and here as well. You will get this result, and further simplification is possible by taking something common from this. For example, 4j is common from here, minus 4j is common here, j7 is common here, and minus j7 is common here. So after simplification you will get this expression. Again, 1 upon 2 is common from these two, and 1 upon 2 is also common from these two, right. So rewriting this expression in this form, now you can see this is actually representation of a cosine shifted by 3 units or delayed by 3 units, and this is also cosine shifted by 3 units. So writing back into the trigonometric form would give you this result. So this is how we can actually find out the response of the system in very easy and convenient mathematical way when we represent the input signal as a combination. That is end of this lecture, and if you have any questions you can ask using my email address. Thank you very much.